Okay, so thanks all for attending this talk, this IAU J1 seminar. So today's speaker is Joel Leja, Associate Professor at Penn State University in the US. He holds the Dr. Kiko Miwa Rose Mid-Career Chair, and he specializes in modeling observations of distant galaxies and data-intensive methodologies. So his work focuses both on the modeling of single individual galaxies, so the use of codes such as prospector you may be familiar with, as well as a study of whole galaxy populations. So Professor Leja received his PhD in astronomy from Yale University under the supervision of Dr. Peter van Dokkum in 2016, and then was an NSF postdoctoral fellow at the Harvard-Smithsonian Center for Astrophysics with Dr. Charlie Conroy until 2020. His work is highly cited, being named Clarivate Highly Cited Researcher between 2023 and 2025, and his PhD thesis was also awarded Yale University's Brower Prize in 2019. So it's a high honor, and it's actually, we're very happy to have Joel here with us. His talk on machine learning accelerated inference of galaxy properties in surveys will surely be of great interest to IAU J1 Commission members. So thanks so much, Joel, and take it away. Thank you.
Lovely. Yeah, thank you for having me here. Thank you for the lovely introduction. Very kind. Yeah, I spend most of my time thinking about how galaxies evolve, and since the launch of Webb, it's been just amazing. I think it's generated a lot of problems, which is great for the field. I mean, so good. But I'll be honest. I'll confess to you that I spend a lot of my time thinking about these problems, but my true passion is in the modeling, building better models, making them faster, better, more accurate. In addition to this sort of breathless science at the edge of the universe, I also spend a lot of my time thinking about these data-intensive methodologies, and that's what I'm going to focus on today. I think in the field of modeling galaxy SEDs, we're still broadly learning how to use machine learning effectively. This field tends to be observationally driven. You build a new telescope, you take new observations, and that kind of is where everyone goes. That makes a lot of sense. I think it's a perfectly good science loop, and we should keep doing it. I think we're having another type of revolution going on right now. We're building these next generation tools, and it is completely changing the way we do observational galaxy evolution science. I used to say it's going to change over the next 5 years. That's no longer true. It's changing right now. I think a lot of this is going to happen over the next 18 months or so. Honestly, really. And I'll show you some of the reasons I think this is true. No one is prepared. I do not think we are generally able to change our workflows over the next 18 months or so in the way that they should be changed. I think this is an area where the more attention you pay, the quicker you'll be able to adapt, and the much better you'll be able to confront the future. Let me just give you one example. What took me 1 million CPU hours on Harvard's brand new supercomputing cluster about 8 years ago now takes one of my graduate students 30 minutes on their laptop. And we are talking about a factor of 1 million speed increase, sometimes more. The speed increases are stunning, but they are maybe the least exciting way to think about the new modeling we can do. I think the exciting stuff we can do is the new science we can ask, the new questions we can ask, and the new directions we can go that were just totally impossible to do. So it's not about doing things faster per se, though we can. It's about asking completely new science questions. I think the 2020s are going to be the era of complex modeling. Let me tell you about it. There we go. Good. So just a quick refresher. This is what I'm talking about here. When I think about galaxy spectral energy distribution fitting, what I'm doing here is taking these beautiful images all across the electromagnetic spectrum. Here's Andromeda from the radio to the X-ray, and turning them into even more beautiful inferred parameters. So measuring things like the mass of stars in a galaxy, the formation history of those stars, the physics of nebula, the dust contents, the chemical abundances, so on, active black holes. So this is the big picture here. How do we turn the data that we have into the physics that we want to learn? I'll just start by laying out a few of the basic modeling challenges as I see it in studying these galaxies. I'm using Andromeda often here, but I'm thinking usually about galaxies at cosmological distances. One of the key challenges in this is that Stars in distant galaxies are almost always unresolved in the sense that the stars themselves are all blended together. So here's Andromeda on the left, gorgeous, lots of detail, lots of individual stars. And then on the right, if you take Andromeda, move it out to something like Redshift 2, you get a kind of unresolved blob, which in this case in Spitzer is truly just a single blob. We have better with Webb nowadays, but that's not the point I'm trying to make here. Hey, my point is that all the time, almost all the time, unless we're working in very, very local systems, we are modeling the sum of the light in these galaxies. And so it's hard to reconstruct things that intrinsically aren't very bright. They tend to be outshone. So this is something we'll think about quite a bit over the next 20, 30, 40 minutes. Okay. Just to spell it out a little bit, distant galaxies are often nearly point sources. So the light from every star, nebula, black hole, etc., it's added linearly. That linear addition is unkind to many things that we want to learn about because they're just not bright. So most of the light that we see comes from a few very bright things, extreme types of stars, black holes that are accreting very rapidly, sometimes nebula. And often what we want to know is not what's bright, but maybe what isn't. And so in that sense, I think inferring things about the distant universe is often heavily influenced or dominated sometimes. We want to avoid that, but sometimes it's true, dominated by our prior. And so, what do bright things tell us about what lurks underneath? And I think this is just a nice example here. Here's a picture of Andromeda in its full scale, full size. It is considerably larger than the full moon, but of course, if you try to see it with your own eyes, it's just a tiny little blotch. We just see the brightest part, the central part. And so, thinking about building models that figure out the truth, even if it's not dominating our likelihood, is something I spend a lot of time thinking about. And so outshining a generic ongoing problem for our field. Another one, and I think this is growing, is just the huge amount of data we have. I'm just going to go through this quickly, but the process of going from pixels to science has a lot of pieces in it, and those pieces are good to think about sometimes. Here's just a raw image, and one of the first things we have to do, this often introduces some of the most controversy, or not controversy, but challenges, is identifying sources. Which of these is a real galaxy? Which of this is a superposition of two galaxies? Which of these is a complex galaxy with a strong color gradient? Which are stars? Okay, often that decision is made well upstream of the modeling process, but you got to think about it all the way down. Um, you have to measure the light from these galaxies. I won't talk about this at all, but they're arbitrarily shaped. They overlap with each other. You have to do it intelligently, and often the best efforts will leave some systematics or some things unresolved, and that's good to think about when you're trying to model those outputs. Interpreting the light itself, I'll spend a lot of my talk today thinking about this, but in brief, if you want my one sentence thesis, galaxies are complex. Our models have these epistemic or systematic uncertainties in them. We're not sure how good our models are, and we have to make guesses anyway. So how do we confront that? And then our data, often weakly constraining. We spend a lot of effort to get these pixels. They're very precious. That doesn't mean they tell us the answer. So good to think about this carefully. Um, and, despite these challenges, which might have you staring at one image for many, many hours as you think about what's in it, what to model it, and what to learn, at the same time, you're staring at this one image, our data volume is growing at a gargantuan pace, just incredible. I remember spending years of my life during my thesis in the early 2010s thinking about seven galaxies. That turned out to be great. There were seven galaxies at Redshift 2. I cared about them deeply. We learned a lot from them. Nowadays, my grad students will think about a minimum of 10,000 galaxies. Many of them will think about millions of galaxies. That number is reaching the billions now. And so we need some way to handle all of these challenges and do it at a massive scale. That's going to be the best way forward. And so it's a good moment to think about these challenges, I think, and to do it good, do it well. Inference in the future kind of has to be flexible, avoiding some of these modeling or epistemic uncertainties, avoiding as much as possible these measurement systematics. The pixel uncertainties are good. It's everything we do after the pixel uncertainties that introduces challenges. And it all has to be ultra fast too. Right? These are tough challenges, I think, to do all at once, but we gotta try. We have to do hard things. So, um, I like to do this all in a Bayesian sense. Right? You don't have to, but I'll make a brief pitch for why Bayesian thinking is really, really helpful for galaxies in particular. Here, this is just showing what a posterior might look like. And the trick is, you don't really need Bayesian thinking if your data gives you a really good answer. If you have a likelihood dominated problem, you don't need to think carefully about your prior assumptions because the answer is right there in the data. No matter what your prior assumptions are, your data will happily drag you towards the truth, inevitably. In that case, we don't need to worry so much about our prior. And there's another scenario where your data maybe aren't informative at all, where you're prior dominated, where your data can't really do much at all. And I call this area theory. Theorists are very important. We love theorists. It's great to have them. But theorists don't need Bayesian thinking because their data aren't helping them, right? They're theorists. And so I think galaxies fit very nicely into this valley between these two areas. The data matter, but the modeling matters and the assumptions matter too. And you kind of have to get both right to get the right answer. So it's a compromise between treating your data right, treating your assumptions nicely, and then hopefully we can weight these properly and get closer to the truth. So that's how I like to think about this. Bayesian thinking is very helpful here because it lets us state both these things clearly and kind of give a push and pull between the two. Uh, so here's just a little movie I have. This is just showing Prospector, the Galaxy SED fitting code that I've spent a lot of time contributing to running. And so on the left, it's I'm just adding in data points one by one. I start with one band of photometry, then I add a second band, and then I have 5 bands, and then I have 10 bands, and so on. And then on the right, you can see a bunch of things that we want to learn. Starting out knowing very little, and then as we add 1 band, and then 2 band, and then 5 bands, and so on, our posteriors start to collapse towards the truth in this case. Okay? And uh, don't worry about all this. It's very detailed. There's a lot going on. All I kind of want you to take away from this is what I have here at the bottom, right? Which is that in this case, I'm fitting something like 18 parameters to one data point at the beginning of the movie, and we get out a reasonable answer. And that answer is we don't know anything except we know the stellar mass to within a factor of 4. Okay? That's sensible. That's okay. We can fit a 18 parameter model to one data point. We can get out good answers. Okay? What we need to do to get out good answers is we need to simulate the correct physics and put on reasonable priors. And as long as we can do those things, is we can write down a good model, we can marginalize over as complex as the universe likes to be and get out reasonable, robust, reliable answers. So that's my goal. All my goal here is to write down a reasonable model, including all of the right physics, connect it to some sampler that can do a good job at exploring posterior space, and then let it go. That's my philosophy. Can we do that? Well, that's what I'll want to think about for some of the talk here. So, Bayesian inference, powerful but dangerous because it lets you think you know what's going on. Right? So, a famous quote, almost too trite to say, but I like to say it every time because if you forget this, you might start believing your results a bit too much. Right? Every model that anyone has ever written down is wrong, as far as I know. But some of these models are very useful. Okay? And so the goal is not to be perfectly right when you write down a model, especially when you're thinking about galaxies. They are far too complex to be perfectly right. The goal is to be right enough to be useful, or not wrong enough to be useful. What does that mean? Okay. Useful means we create new knowledge, we learn something new about the universe, we can tuck it away in our toolbox and forever say, star-forming galaxies have emission lines, or whatever we might want to learn. But to get to useful, we have to do a lot. We have to understand our data very well, our measurement uncertainties, our instrumental effects, and so on. We need to have reasonably accurate generative models for what we're fitting, stars, gas, black holes, dust, so on. And if these things are not true, you really should be careful. Modeling can do more harm than good. Sometimes you might think you've learned something very, very well, And what you've learned is actually a mirage created by your model not working that well. Right? So that's something we want to avoid. So, are we there? Are our models accurate enough to be useful? Well, that could be an endless debate. I'm going to show a few slides that are recent results from Webb that seem to have very surprising results and I think highlight some gaps where we can think more carefully about our models. Maybe our models are doing just fine and the universe is doing something extraordinary, or maybe we need to go back to the drawing board on a few pieces. So just a few results from Webb to get you thinking here. One is the stunning number of very bright, very dead galaxies at redshift 4 to 5. Here I'm just showing one from the Rubies survey. This was an extraordinary object. We found it a couple of years ago. It was published last year in Nature Astronomy. It has a gigantic Balmer break. It is at redshift 4.9. Okay. And it's just overall a stunning object. I mean, just a beautiful spectrum from James Webb. Something like 45 minutes of this telescope gave this lovely spectrum at redshift 5. Um, this thing is tiny. It has a effective radius of about 500 parsecs, and it's something like 4 times as massive as the Milky Way. So it's an incredibly dense object, incredibly dead. But if you fit it as we normally would a distant galaxy and try to interpret it, in this case using Prospector, but it doesn't matter. I'll show you results from many different groups in a second. Okay. If you model the rest frame optical data, this is a plot showing how much mass was formed as a function of time. Um, Everything up and to the left of the epsilon equals 1 line is a big no-no. This means that we are turning all of the gas in our halo into stars, and anything to the left of the line means we're turning more baryons than should exist in our halo into stars. Okay, so this is one of a class of objects where we are forming galaxies way too efficiently if we trust the results of our fitting. In this case, I'm showing you two different solutions, one in purple. This is what happens if we just let the fit run and don't think about it much. We just fit the data as they are. Out comes an answer, and the answer does seem to break our universe if you take it seriously. I don't think it's right. Don't get me wrong. I think it's wrong. And the other answer in light blue is if you are a bit more heavy-handed and you say, well, maybe we should force this to have, in this case, something like a solar metallicity, which is what we expect if this galaxy forms uh, so many stars over such a short period of time. You'd expect to produce a lot of metals. In that case, we no longer violate our baryonic budget, but we still form uncomfortably fast. 20% star formation efficiency means 20% of the baryons in our halo have turned into stars. Compare this to the Milky Way, which took the entire age of the universe to do 5% of the baryons in the halo. So this is just a stunning result. It has not really gone away. I think you can chip at it a bit, but even with bringing out all the stops, you end up with something like 10 or 20% of the baryons in the halo have to be in stars. Um, is that real? Is that how we should really accept things, or are we making other kind of epistemic mistakes? And I think the answer is a bit of both, which I won't get into too much. But this has really driven a lot of my thinking. I think we need to build better models to really understand and grasp this kind of results. Okay, so this isn't illegal in Lambda CDM, but even the late forming solution is uncomfortable. It really challenges a lot of our thinking of how quantum galaxies formed. Hey, and just to give you a flavor for this, this is not just in the Ruby survey, this is not just Prospector, this is kind of across the board. Here's a bunch of results from Adam Carnall's work of similar types of galaxies, which all have similar types of problems. And I'm not even showing you the most extreme one. The most extreme one is probably Carl Glazebrook's work in 2023, which requires forming like 10 to the 11 stars by redshift 14-ish. That one is a stunning result. There's got to be something wrong with the modeling, I think. But even if you have a factor of 5 or factor of 10 problem in the modeling, it's still an extraordinarily fast forming, early forming galaxy. So this result seems to be across the board, um, requiring a change in how rapidly we form these massive galaxies and stop their formation. And if you don't do the modeling very, very carefully, you get seemingly incompatible answers with lambda CDM. So this has been a delicious problem to think about. Lots of fun. There's other big challenges in the early universe. So preposterous, or is it? Again, I think it's a bit of both. There's other just fascinating things in the early universe. I'll just go over these quickly. They're not the point of the talk, but they really help motivate my thinking and drive me here. One great example is from Harley Katz over the last couple of years, who has found some 100 objects in early Webb spectroscopy where normally we expect around the Balmer break region to have a flat SED, i.e. no Balmer break, or a small break, indicating older evolved stars. Harley has assembled a large sample of objects which appear to have a Balmer jump. Um, this is hard to produce for reasons I won't get into, but in brief, you need to have a huge number of ionizing photons. Um, and the nebular continuum needs to be a dominant or maybe even the only significant component emitting in the UV. It's hard to have a large number of ionizing photons and not have those sources producing the ionizing photons be super bright in the UV too. And so some of these you can model by almost an instantaneous burst of very, very young stars. Some of them you might seem to start tweaking things that we don't like to tweak, things like the IMF, things like hiding black holes that only emit through their ionizing photons, or exotic stellar models, balls of Wolf-Rayet stars. I don't know what the answer to these are, and I've thought about how we can solve these with normal stars, but I don't know if that's actually satisfying at this point. The number that Harley finds of these and other surveys find keep going up, and the unusual circumstances required to produce these with normal stars and other types of funny geometry are getting more and more contrived. So I think there are big challenges on the nebular modeling side too, and that's very, very fun. I think this is something that is ripe for a huge amount of disruption, and I'll talk about what we've thought about a bit. Okay. One more thing I want to touch on first. Bursty star formation is seeing a real heyday now, thanks to a lot of early surprising findings from Webb. And I've listed some of the papers from this here, but there are many more, many that I couldn't cover, so I apologize. But in brief, we find a lot of these very low mass galaxies at high redshifts where all low mass galaxies should be star forming. And instead of being star forming, they often have these baby little Balmer breaks, or even sometimes larger Balmer breaks, indicating that they've been dead for some 20, 30, 50 million years. And the way people have found to explain this, they shouldn't be permanently quenched, but instead maybe they're having some giant burst of star formation, consuming or expelling all of their star-forming gas, and then briefly turning off before they're able to get new fresh gas in. Um, this is, I think, a fair description of what's going on. It seems very likely. It is a real pain to build SED models that can do this gracefully, largely thanks to the outshining problem I mentioned earlier. Um, so I'll talk about some of the very significant challenges that exist in a universe where bursty star formation is common, and how I think we might be able to get around them. I think this is going to take a lot of work, and it's a very fun problem to have. So it introduces a lot of physical questions, and it introduces a lot of modeling challenges, right? So we can solve this by doing very careful modeling, though, right? Probably, maybe. Okay, I'm going to talk a little bit now about some of the challenges I see in the modeling side. Okay. This is from one of my favorite recent papers by Cami Pacifici, who got together a huge number of people who do this SED modeling of distant galaxies. Incredible work. And so she performed this experiment where she took these 13-ish codes and 13 groups doing this work and applied it to identical, high-quality, rest frame UV to near-infrared space-based photometry. Fantastic stuff. Very good data. She had everyone fit these data and then just report the results. Okay. And so here is one of the figures from this excellent paper in 2023 that did not make it into the paper. And so this is just the star forming sequence, the mass versus the star formation rate for all of the galaxies that Cami had us fit. And there are 13 different codes in here. The color coding is by dust, but don't worry about it. It's not really highlighting anything particularly interesting here. Um, the line in every plot is the same. It's just to guide your eye. And so uh, the results from these different codes are very, very, very different. And we have quantitatively and qualitatively different galaxy populations. Right? The location of the galaxy star forming sequence is different for every code. Right? Sometimes the population is above the line, such as with Beagle. Sometimes the population has a large scatter around the line, such as with Prospector. Sometimes the population is well below the lines, such as P12, which is Cami's code. Right? The amount of scatter around the star forming sequence, totally different in every code. Prospector gets a huge amount of scatter. Something like Beagle or Seagal in particular gets much less scatter. We have different quiescent fractions in every code. Some codes have very few galaxies far below the star forming sequence. Some have a lot. Maybe the thing that's the most different is how dead are dead galaxies? Are they sort of interspersed between the star forming sequence and down? Is there a big cloud? Do they sit way down at the bottom? Are they all very dead? Everyone has a different answer. And so I show this because it's very puzzling, I think. And all these people are smart people with good ideas about what's going on. Okay? These aren't bugs or small things. This is a real challenge for the field. This is not a simple problem. Okay? So why? What's the issue? Let me show you another example of this, and this one I find much more troubling and was much more, well, it wasn't as well advertised, I'll say that. You might say, fine, photometry. Everyone knows you can fit anything to photometry and get a great result, perfect chi-squared that is totally different from what you did last night. Photometry is pretty degenerate. We know that. What about spectroscopy? Even better, what about the best spectra I've ever seen of distant galaxies? So this is from the Legacy survey. This is from the VMOS instrument on VLT. A huge amount of time invested in this survey. These spectra are beautiful. They have cellular noise of 20 to 70 per angstrom, not per pixel, per angstrom, at R of 3500. These are rest optical spectra, and they are just stunningly high information content. Right? This is a totally different game than photometry. We know so much more. How do we do? Do we have the same problems? Well, this came out. Sorry, I should have updated. This is from Anna Galatsi's work. It's now published. It was published a couple months ago, so this is a 2026 reference. But I think this is Appendix E of this work, where Anna, me, Adam Karnal, a few other people spent a lot of time in a basement in Ghent, Belgium, fitting these spectra with our different codes, just fitting them over and over and over, and trying to figure out why we keep getting different answers. We never got a satisfying conclusion. That's why this is in Appendix E. And so here, this is the results from stellar metallicity and from light-weighted stellar age. So stellar metallicity at the top, we have Prospector versus BASTA, which is a Lick index-based version of finding metallicities. And then in the upper right, we have bagpipes on the y-axis versus Prospector on the x-axis. These are metallicities from beautiful absorption line spectra. No one agrees. There's not even a one-to-one cloud here. Right? We're not even close to agreement. I was stunned by this. Metallicity, I thought we could get right with these beautiful spectra. We can't. And then in the bottom is a log of the light-weighted age. Light-weighted being what is the average age of the light we collect. So not worrying about mass-weighted age, not worrying about our different priors. It's still pretty dang unsatisfying. Okay? We don't even really agree on the light-weighted age. Not that well. We should be doing better. The mass-weighted age looks much worse. Okay? So it's not just photometry, it's spectroscopy. We do not agree, even though these are brilliant people doing their absolute best. Right? No one's making a simple mistake here. Why? What's going on? Why can't we agree? All right, here's my thesis. Okay. I do not think we yet include enough physics to model the complexity of galaxies. And galaxies they're just complex systems. There's a lot going on. I will briefly show you a movie illustrating what I think are some of the many things we are worried about that we're not always modeling in here. But I think this is the basic challenge. There are so many different physics at play when we are modeling these systems. We need to make approximations, we need to make assumptions in order to make this tractable. And every time we do that, we create these systematic uncertainties that move us irrevocably, inevitably far away from the truth. Right? We're creating these systematic uncertainties because we have to. But it means that we get these disagreements that we just can't adjudicate very well. Okay? So I'm going to play a little movie. On the left is an example of a physical parameter that affects our SED. On the right is the approximate size of the effect on the SED. And I'll just play it here. Yeah, so I stopped it due to time. There's a lot going on. There are so many things we need to worry about. Okay? And many of the things I'm listing here are not one parameter, but they are many parameters. For example, the stellar abundance pattern, which I suspect is a large part of what's driving the disagreements in the metallicities from spectroscopy. That is at least tens of parameters and probably more. Okay? So many of these things are not well treated in our codes, but we have to worry about the many. And so I think we have to get better at this. So what's the problem? I just wrote down all of our problems. Why can't we solve them? Well, this becomes a computational issue. Our current modeling, we're already hitting these hard limits. And so once you get past something like 8 or 9 parameters, you suffer very greatly from something called the curse of dimensionality. It's a technical term. I'm not being mean. Okay? And so that means it's just hard to fit everything on a grid. If you want a 15 parameter model with 10 values per parameter, you need an entire data center just to write down your models. It doesn't work. And so in high dimensional fitting, if you want to include a lot of stuff in your fits, like a 20 parameter model, you need to generate everything on the fly. This becomes a very compute intensive task. Right? Something like 15 hours per fit. You just want to run something like FSPS or BCO3 every time you want a new galaxy. It's expensive. It takes several million CPU hours to analyze a typical extragalactic deep field. So we have to do better. We have to go faster. What does that mean? And what's driving the computational requirements? Well, I'll just walk you through it. You start out with observations. Building a model. I've spent many months of my life optimizing this building. Still, we can generate something like 20 models per second. Pretty fast. Pretty good. Okay. You need about 1 million models per fit, though, to get a good fit. So 20 models per second times 1 million models required. That's how you get to 15 hours. Okay. Hard to get around. This is just kind of the state of things. So how do we beat this? How do we do better? I'll show you a few ways we can make this faster. One thing we can do is build something called a neural net emulator. So we take these complicated stellar populations codes, doing all of these very complicated stellar atmospheres and stellar isochrone calculations. You replace them with a neural net, which just says, give me the inputs that you want to specify, things like your star formation history, metallicity, and so on. And then I'll give you the outputs, and we're just approximating all the calculations. It's a bit of a black box. But neural nets have taken on some popularity in the last 5, 6 years. And they can speed up our model generation time by something like a factor of 100 to 1,000 or 10,000 on a GPU. And so we've thought a lot about this. This work has been done by one of my grad students, Elijah Matthews. I'll just show some of the things we've learned here. Neural nets are very fast. They get to this speed with a basic trade-off between flexibility and precision versus speed. And so the bigger your network, the faster you can evaluate it. At some point, your network gets so big, you're running as fast as the original stellar populations code. That's not good. Okay. The bigger your network is, the more accurate it is. And so you want to have a sufficiently small network that you can be fast, but a big enough network that you can be accurate. That's kind of the goal here. And so, one advantage also of having a neural net is that it's differentiable. And that's super nice because you can get gradients of the likelihood. I'll talk about that in a second, but that lets us do some very fancy sampling. We don't need to do MCMC or nested sampling. We can do something much faster if we have a gradient. We get those for free with emulators. This is an example of what a gradient lets you do. A normal blind random walk will kind of walk randomly around towards the solution. It gets there. It's not very efficient, but it gets there every time, so they're popular. If you have a gradient, you can do something more like this. You can follow the curve right down to the truth. All right, so gradient-based samplers are much more effective, and you get those for free with an emulator. And, and so if you think about this a lot and do some tests, you can show that emulators give results that are just as good as our classic approaches. You have to do some tuning and think about what it means, but here we're just showing if you run the old on-the-fly approach versus our new emulators, we get the same answers for things like dust and for things like mass. And that's been fantastic. If you think about it carefully, you can get good results. And our rule of thumb has been as long as the emulator uncertainty is a factor of several below the observational uncertainties, that's a totally fine trade-off. And so we aim for emulators that are precise to 1 or 2%. Okay. So these emulators are fun. They let us do all sorts of things we couldn't do before. So this is an example. This is from one of my former postdocs, Bingji Wang. She's a Hubble Fellow now at Princeton. She left a couple months ago. But here she was modeling some of the first deep fields from Webb, in this case Uncover. And she fit something like 70,000 galaxies here with these complicated models, something that would have taken me months as a postdoc. She can do it in a couple days. And we did it many times to discover all sorts of different things. In this case, this emulator, this neural net emulator, picked out two candidates that turned out to be the second and fourth most distant galaxies known at the time, confirmed by spectroscopy a few months later. So this neural net emulator found a range of 13 galaxy, something we thought was really cool. You can push this further, and I won't talk about this much, but if you care for speed, the most efficient version of this is something called simulation-based inference, where the stellar populations models we've been using are the simulators or the generators. You train it on noisy data and the true parameters. So this is work from one of the students in my group, a statistics student, Leja who was able to get a simulation-based inference approach. She trained it on Prospector. It does everything Prospector does, except it does this all 1 million times faster. And so this little movie is just showing you, normally we'd take something like 2 days to do a really, really, really good fit to photometry. So the red bar is how long a nested sampling fit takes. And the blue bar is how long or how many objects we can fit with simulation-based inference at the same time. SBI can do 2.5 million times faster than normal Prospector. It is a stunning result, and the posteriors are just as good. Actually, they're a little bit better. So simulation-based inference is cracking wide open all sorts of problems that were completely impossible to even think about nowadays. This has been the most exciting thing. I don't want to talk about it anymore, but if you want speed, we have that in spades now. Computational limits are, well, when you have a 2.5 million speed up in a couple of years, you can do a lot more than you could before. I've just been stunned by this result. All right, fine. So we can do everything we did before much, much faster. But faster isn't a virtue on its own. We can also do completely new things. And I'll tell you a few things that we're doing that are just completely new. So things like forward modeling imaging, you can fit hundreds or thousands of pixels at the same time. You can do population modeling. You can fit thousands of galaxies at the same time and learn qualitatively new things. Or we can build these very, very complex models where we can learn or marginalize over all these things that we're worried about. Hundreds of models or hundreds of parameters and things like AGN, stellar evolution, chemical evolution, and so on. So I'll tell you about some of the things we've been working on that are moving in this direction of doing much more complex, much more sophisticated physical modeling. And it's so much fun. It's just been a lot of fun. So I'll talk first about some spatially resolved stellar populations modeling. And remember, distant galaxies, we tend to treat them as unresolved. We draw a circle around these things, add up all the flux, and call it a day. That's not how they work, of course. We can actually see some structure. Uh, If we wanted to, we could fit a complicated model to every single pixel we see. This has a lot of advantages. We can remove all these intermediate layers of analysis that create systematics. We can do much better at breaking some degeneracies. We can see old stars where they are. We don't need to worry as much about outshining. Here we can see the old stars in the bulge of Andromeda. We can measure things much more precisely, and there's been a lot of work done moving in this direction. Uh, the key challenge that I see it in this field is that you can't actually fit every pixel independently. The pixels have been correlated by the point spread function. And they're all correlated. And so, really doing this right, you can't treat every pixel as an independent galaxy. You need to fit them all at the same time. You need to build a model for what the galaxy looks like and then smear it by the point spread function. This makes the problem so much more complicated because you need to model hundreds, thousands of pixels at the same time, at the same time. Okay? That's what you need to do to treat this properly. That's a much higher bar. Okay? However, we can do it. I just told you how much faster things are now. And so this is work by one of my students, Elijah Matthews, who's been building a modeling tool for this problem. So now at this point, we can forward model photometry of any resolution in the native pixel space. We can propose a model. Every pixel has its own 15 or 20 parameter physical model. And then we predict the light in all of these pixels, and then we smear it by the point spread function. In some case, if you're fitting low resolution or photometry, like from Spitzer, this means everything's a blob. That's okay. Okay. And so right now we're just fitting our normal galaxy models to every pixel, smearing it by the point spread function. We take advantage of these neural nets that give free gradients, and so we can use these complicated samplers that are much more accurate and faster. What does this mean? Okay. You can fit a 75 by 75 pixel image with 20 filters, in this case web-based. This fit will finish between 10 and 30 minutes, or 10 and 300 actually. We're still working on the sampling. Some of these things are more complicated. To be clear, this is about 84,000 free parameters. And you can finish a fit, most of them finish in 10 minutes. Ridiculous. Okay? This would take something like 100,000 core hours in our classic approach, and it would never converge. It would never converge. Okay? So, does it work? Yes, it does, though we found some interesting challenges. So first off, you can run these fits for fantastic galaxies from Webb. This is a 20-band photometry from Webb, and you get these beautiful, spatially complex stellar populations. You get these lovely metallicity gradients, these big, complicated mass profiles, and they look great. They're so interesting. So this part works very well, and it works very fast. Our uncertainties get so much better if we fit every pixel. Typically, when we fit unresolved photometry, we'll get uncertainties of 20% or 50% on the stellar mass. This is very good. This is a great outcome. Now we're getting uncertainties of a few percent from spatially resolved modeling. And our mock test suggests these are well-calibrated uncertainties. So those error bars are correct if our model's correct, which it seems to be pretty dang good. So we can measure things much, much, much more precisely, which has been a lot of fun. Right? Why aren't we doing this for everything yet? Well, I think we will be soon, actually, and people are heading in this direction. But I will say, hey, we can run better fits, but we're also exposing ourselves to new degeneracies, which are going to take some time to wrap our head around and treat properly, I think. Let me just show you. Here, this is a galaxy from Webb. I'm just showing you a PNG. The observed one is in the lower right. The other five are model fits, where we just make different small assumptions about how the metallicity and dust is distributed in the galaxy. You can't see the difference between the five model fits because, well, they fit to basically machine precision here. They're all perfectly good fits. They're indistinguishable in a chi-squared sense. Here on the right, this is the posterior for the stellar mass formed in each of these objects. And if you can't read the axes, I'll just say there's something like a factor of 5 difference in the recovered stellar mass, despite all of these fits being beautiful and very, very good in a chi-squared sense. Right? So uh, this point spread smearing, smearing by the point spread function, doing this forward modeling, we have to do it. It's what our data do. We can do the fits now. We have the technology to do it, but it introduces this new uncertainty. How are dust, metals, and stellar populations of different ages mixed in our images? We need this industrial scale calibration using, I think, spectra that we just haven't been able to get our hands around yet. So I think this is very, very powerful, and we're still learning how to use it. Right. So spatially resolved modeling, I think, is very fun. I'll talk a little bit about nebular modeling as well. Right? So star-forming regions have these giant, complex gas pillars. In this case, this is the Eagle Nebula. Right? These have complex physics. We often model them with something photoionization codes, cloudy mappings, other codes. They themselves have hundreds of parameters in them. So they're complicated on their own. We can't really run a cloudy model every time we want to model a galaxy. It doesn't work. Galaxies themselves, of course, also have hundreds of thousands of these separate regions, which make it a complex problem, just very hard. So we try to make this a bit more robust using something called Q. This is a neural net emulator for photoionization models. Okay. Here, what we did was we ran cloudy millions of times, and we put in an arbitrary ionizing spectrum, just a power law spectrum with different breaks. We learned how to build nebular models of our different galaxies that can be ionized by anything, stars, black holes, other things, as long as you can describe it with the power law, it works great. We replaced cloudy with a neural net emulator again. This is a little video of Q running, where it's just proposing different types of ionizing sources in a galaxy until it's able to match our data in the upper right there, which are large numbers of observed emission lines. And so Q can predict something like 130 different emission lines to better than 5% uncertainty. Importantly, each prediction takes about 5 milliseconds. So it's something like a 10 to the 4 times speed up from our raw photoionization codes. So we can run this in real time. Again, we can strap this to our samplers and let it go. This has been a ton of fun. We can move away from grids and do real, complicated science. We can investigate mysterious ionizing sources or marginalize over uncertainty in things we don't know if our data aren't so good. This tool has been a ton of fun. I'm running out of time, so I'm not going to show you any of the examples here. It's been used at the edge of the universe a number of times and has found all sorts of fun things. And so these are the two most distant galaxies where Q is used, and it's found some surprises. It's been great. I will spend a couple of minutes here at the end talking about spectra, and then I'll wrap up. We have a lot of new spectra coming in from these surveys of the observable universe that are super, super helpful. So things like DESI, Euclid, PFS, Roman. We're going to be in the tens of millions of spectra over the next 5 or so years. I'm just showing here. This is one of the ones I'm involved with, PFS. It is a huge field of view. I'm skipping some of this so I can get to the science. Here, we can also play the same game by emulating spectra. And we can get very, very fast fits to spectra as well. This is led by one of my students, Emily Burnham. Turns out spectra are very easy to emulate. You can get precision of much, much better than 1% very, very quickly. And so these spectroscopic emulators are very fast. They scale very efficiently on GPUs. This has also been a lot of fun. It's harder than photometry, but more rewarding. One other thing we've been trying that is kind of qualitatively new with this is instead of fitting spectra fast, what we can instead do is fit populations of galaxies at the same time. And so I'll tell you a little bit about why this might be useful and what we might learn. I mentioned earlier that bursty star formation is kind of a pathological challenge to our models. And so that's because it has this outshining effect that basically totally obscures the history. And so we showed this in a model space where we generated a perfect spectrum, very high Silicon noise, web spectrum, perfectly fitted with a bursty input star formation history, this dashed square line here in the middle panel. And then we fit it with a flexible star formation history. That in this case is a continuity prior. It doesn't like to change its star formation rate very much. And it has no bursts in it at all. Yeah, even though we fit the data perfectly, no bursts. We recover nothing. Okay. If we go back and instead we tell the fit, hey, this galaxy should be bursty. There should be a lot of bursts in it. We get the result on the right where we have one single burst and nothing else. Okay. So this problem can't be solved with one galaxy alone, I think. Outshining makes it just too dang hard. Okay. And so this degrades our results a huge amount. We're systematically wrong by factors of two or more if we try to do this for a single galaxy alone. It's pathological. Um, so if single objects are degenerate, we can do something else. We can fit entire populations at the same time. And, and so that's something one of my students, Emily's, worked on. She had a paper come out recently doing this, where she can write down a model for an entire galaxy population, all of which are fluctuating up and down at some level. And I won't describe the model we use to do this, but in brief, it's a power spectrum of fluctuations. It's like how we model the CMB. I think it's very nice, compact mathematical formalism. And then you can simulate populations of galaxies that have certain levels of fluctuations. And you get different distributions, in this case, of observables. So different distributions of H alpha fluxes, different distributions of UV fluxes, of Balmer break strengths, and of optical rest frame colors. And so we can get around the speed requirement here by using simulation-based inference again. So we model huge populations of galaxies and we train a simulator to do this. This makes this whole process run in seconds in real time. So we can do this super, super rapidly. Okay. And I'll just show some of the results here. This is a power spectrum density plot. Here we put in some fire-like population, very, very, very bursty, and we show that we can distinguish it from an illustrious type population, which has a much smoother star formation history. And we can do this with about 500 JWST spectra. It's actually very cheap. Okay. And so this forward modeling approach, where we fit entire populations at the same time, lets us measure burstiness extremely well. And suddenly we can distinguish quantitatively and powerfully between hydro simulations with very different models of how bursty or how flickering these galaxies are. And the trick is we don't fit one galaxy. That's impossible. You fit thousands at the same time. And we can do it with these tools. And so this is an example of something that was, I think it was unsolvable something like 10 years ago. And now we can do it. We can do it with these new modeling approaches. Everything's so much faster and so much more sophisticated. We can fit everything at the same time. And it's been a lot of fun. And so we're building more sophistication into this, trying to model our observational selection functions better, trying to fold in some of these fundamental stellar physics uncertainties. So do we use BPAS? Do we use FSPS or something like this? But that's what we're working on now. And so this population modeling, I think, has enormous promise. Okay, I'm going to wrap up just to bring you all together here. The amount of time it takes to fit a galaxy broadband SED using on-the-fly stellar populations. In 2017, right after I got my PhD, it took something like 100 core hours. It was very slow and usually wrong. A couple of years later, we spent a lot of time optimizing. We got it down to 20 core hours. We could feel the wind in our hair at this point. It was very exciting. 2021, 2 years later, we got down to 10 core minutes using these neural net emulators. 2024, if we strap it into a GPU, we can get another factor of 10 out of this. People like Andrew Herring and Justin Olsing have done a lot of work on this. And now simulation-based inference yields something like less than 10 core seconds per object. And to be clear, that number is inflated by about a factor of 100 from what we're doing right now, which is more like 0.02 core seconds per object. Okay. So this is a 10 to the 5, 10 to the 6 speed up in the last 5 or 6 years. This is a huge sea change in the field. we can build these very, very, very complicated models. We can fit them very, very quickly. And the last thing we need at this point, we just need to find the right problems and the right way to write down the problems. We can do so much more than we could before. It's a new era, and it's been a ton of fun. Okay, so I'm going to wrap up here. Just leave my conclusions here, talking about some of the ways we sped things up with neural net emulators, with simulation-based inference, and some of the new things that we've done with them, like population modeling, spatially resolved modeling, and much more sophisticated nebula modeling. So thank you.
Thanks so much. Let me just change the. Well, fantastic. That was a brilliant talk. I really love your enthusiasm about all this. This is really amazing. And as you say, it is absolutely impressive the way things have been evolving, because as you say, many years ago, things, even with the models themselves, I mean, you can imagine the type of models that people were playing with even before your PhD were absolutely simplistic, and things are getting to that level so I have a good number of questions, but I want people here to take advantage of you here to ask questions. So please, I mean, we don't have so many people here, so please basically open the mic and perhaps open your camera as well if you want to ask a question. Yeah, Thaisa?
Hi, Joel.
Hi.
Thank you so much for your presentation. Very impressive. Congratulations on your work. I'm curious about, the combination of emission, gas emission, and stellar population. Because when you look at stellar population, you have some tools, and then you have the gas emission, and the physics has to be in accordance to each other. So yeah, how to use one to constrain the other. The modeling does that, or it's
Yeah, I think it's a great question. I think this is one of the frontiers is classically these things have often been treated separately just because you get absorption lines when you have old stars and you get emission lines when you have young stars, and it's hard to mix the two. I think there's plenty of opportunities for combining both these things, and we should. Um, so this is something we've been working on. In my case, I've been in my group, we've been combining these neural net emulators of photoionization codes like Cloudy, and strapping them into things like Prospector that fit all these absorption lines and fit all these star formation histories together. And so a few things we've run into immediately is that metallicity in the gas means something very different than metallicity in the stars, of course. And you immediately need to start worrying about abundance patterns, where we're kind of measuring oxygen abundance and some perturbations in the gas, and we're measuring something like iron in the stars. And so including alpha enhancement has been a major step forward for us. Um, One of the key challenges that we've been running into is I don't know how the gas phase metallicity and the stellar metallicity should be coupled. Um, should the young stars have the exact same metallicity as the gas? Should you allow some
long
scattering?
time ago, I did a work with UV spectra from even IUE.
Yeah.
And we had also, we could calculate the metallicity of the gas and the metallicity of the stars. And there was a correlation in the
Ah,
UV. Okay.
good.
Yeah. But yeah,
I'd
it
love to
was
hear more
something.
about that. Yeah,
Yeah.
we're
Yeah.
you get very different answers if you tell them to be tightly
Yeah.
coupled, if you have a lot of scatter.
Mm-hmm.
I think it's a rich field, and
Okay.
there's a lot to learn. But that
Okay.
that
Yeah, because yeah, you showed some spectra with the Balmer breaks that, for me looked like maybe the emission lines were AGN. So you had this doubt it was AGN or not AGN, but the emission lines maybe could tell you. Yeah. So
yep,
it's nice
yeah,
ideas.
yeah,
Okay.
totally. Yeah, that's another
Okay.
axis of uncertainty. Whether you force the stars you see in the continuum to ionize the gas, whether you let there be other things. So with
Okay.
Q, we can
Yeah.
add an AGN and a stellar component, and it's fun.
Okay. Thank you. Thank
So
you.
Thank you.
uh, I have a question for you, Joel, regarding, I mean, the introduction was really nice. I really enjoyed it because you were basically poking your finger at the big problem we have in terms of the degeneracies. And it takes a lot of time, but then you need to do the modeling. But then the results that we're getting, I mean, even when you're comparing metallicities from different models, the work of Camila Pacifici, you could see that it was so, which was a really nice exercise. So I really like it a lot to see it in your introduction. So now my question to you is the following. You very nicely said, look, when we go from photometry to spectroscopy, we add so many more pixels of information. We have so much more, but nevertheless, we don't get so much better. I mean, you would imagine that when you go from photometry to spectroscopy, your timescales would be fantastic, your stellar masses would be super accurate. So how do we learn this? I mean, I like the way you put it. We need to put more physics, but now playing devil's advocate, I would say, even if you put those too many things, it's so degenerate. It's like the central limit theorem. You won't be able to learn anything from it. So can we use something like explainable AI, some way of trying to see how these things learn, to see what is important information, let's say in the spectrum?
I love this question, and that particular comparison is the one that haunts me the most. That was my favorite figure of 2025, even though it's Appendix E, um, because it's such a good challenge. And
Yeah.
so here's some of my answer to this. All we're fitting there are stellar atmospheres. When we're fitting the continuum, in that case, we're finding galaxies without AGN and without significant nebular emission. These are just stellar atmospheres. We know how to fit stellar atmospheres in the Milky Way. We have these industrial scale surveys of stars where we can get abundance patterns and ages down to a few percent.
Yep.
And everyone agrees on them. Uh, so that problem has been, I think, effectively solved in our own galaxy to the point where people are doing things like chemical tagging or talking about doing them. I think it's impossible, but anyway. So people can solve stellar atmospheres when they're single stars, but somehow, if you combine them all together in a galaxy, it becomes an impossible problem. So I think that is a solvable leap. And so what I'm thinking about now is how can we do a more controlled experiment where we go from labels of stars that we know in the Milky Way and add them up so we have millions or billions and then get a recovered good metallicity? So I think it is a crazy thing that we still don't have a good answer to this, but I think that one is solvable because we understand stellar populations and there's something going wrong in the way we sum them. I have a few ideas, but
So you
I
feel
think about it
positive.
all.
It's good. It's good to
I'm
hear because
positive.
I tend to be too negative. Perhaps I'm getting old now saying that the mixture, I mean, and the problem is because the way you put it, if you have a single atmosphere of a star, you can actually see, I mean, you can observe the spectrum of a star to a resolution 100,000 and you will learn a lot from it. Whereas if you do exactly the same experiment in a galaxy, because of the kinematic kernel, you kill a lot of information. And the question is, do we kill it in that regard or can we actually extract information? I think that's but I like to see your positivity. Actually, it's actually very good to see
Good.
that.
Yeah, great. Don't ask me about black holes then. But yeah,
Okay,
that
are there
problem's solvable. Yeah.
are there any other questions? I would put one more final one, given that. So when you're actually were mentioning initially in the first part of your talk, these very interesting galaxies that are very massive at relatively very high redshift, and you would say because basically because of the look back time, these objects are young enough that in a sense these degeneracies are easier to deal with because you're getting rid of the typical things that you find in older populations. So now could you still take it to the limit and say the stellar masses could be very wrong because the IMF or something else is producing this so that it's not so crazy? You don't have such a high mass in such a small thing. I mean, could you still have that possibility or is it ruled out?
Yeah, so that's a great question, and one of the things I think about the most when fitting these high redshift quiescent galaxies, because you can make the IMF more top heavy or less bottom heavy, really, and you can solve all these problems, right? And it's a very attractive solution. The IMF should vary. Everyone agrees. It should vary. Um, The problem is these high redshift galaxies, they're so massive. They're already 10 to the 11, 2 times 10 to the 11, 3 times 10 to the 11. We see these things in the local universe. They are things like M87. Okay? We see the stars. They are alpha enhanced. They're very old. In the galaxies that we think these massive quiescent galaxies turn into locally, they seem to have a bottom heavy IMF. They
Yeah,
have the
yeah,
other thing. And
yeah.
so that would suggest these galaxies at high redshift, if we treated the IMF as we think we should based on local measurements, they should be even more massive. And so opening that door, I think, well, to me, it creates almost more problems than it solves. But we kind of have to do it because that's what they turn into, right? And so people have proposed the ski slope IMF, which is both bottom and top heavy and kind of barely solves some of
Yep.
this without adding more mass. That's maybe one way forward. But yeah, the IMF is not a free lever for these things. And I don't know which way to turn that lever to make all these data points fit. I'm not sure. Probably it's different, but I don't know how.
Well, the good thing we would say is that we're in a fantastic time where there are so many things that have to be explained. Otherwise, it would be boring, wouldn't it?
Yes, I'm having a great time. Yep, problems are good. Problems are good.
Excellent. Well, great. Thanks so much, Joel. It has been really nice. I mean, as you know, we will put this in YouTube, and I hope many graduate students get to see this talk because I think it's also very pedagogical. Really nice information here. So thanks so much, Joel, and take care. Yeah.
Thank you. Thank you for having me. Take care.
Best wishes. Bye
Everyone.
bye.
Thank you.